Asma Hassannezhad from University of Bristol, and she will speak on the geometry of small Laplace and Steklov Eigenvalues. Asma, you're welcome.
Thank you, Michael, and I'd like to thank Katie, Luigi, and Matteo for organizing this wonderful workshop, and thank you all for coming. What I'm going to talk about is some connection between the geometry of our underlying space and so-called a small eigenvalue. So I'm not assuming that you're familiar with the topic, and my talk is one of the few talks that will focus on related topics. So let's first fix our setting. So there will be, as the title suggests, two eigenvalue problems, Laplace eigenvalue problem and the Steklov eigenvalue problem. So for the first half of the talk, I focused on Laplace eigenvalue problem, and we review some of the classical and more some recent results. And what is our setting? So for the purpose of this talk, so our underlying space for the first half of the talk is a closed, connected, oriented hyperbolic surface. So here, let's put G, and G is always my hyperbolic metric. So many of these conditions we can relax, so closed means compact without boundary, but we can relax this condition. Most of the results remain true. If I assume finite volume, complete, connectedness is kind of natural, but hyperbolicity also we can relax a little bit. So you can think of sigma as, so everyone knows upper half plane, you can think of as a quotient of upper half plane by some discrete subgroup of the isometry of H2, SL2R, and then our metric then looks like this, and our operator is in this coordinate will be this. So we are interested in the Laplace eigenvalue problem, which is, so we study this eigenvalue problem. And because our manifold is closed, so we have discrete set of eigenvalues. It's connected, so we have constant function with multiplicity 1 correspond to 0 eigenvalue. And then we have, let's say, lambda 1, lambda 2. We may have some multiplicity, and so on. So what we mean by a small? So I think this term was coined by Huber in 1961, even though the interest in a small eigenvalue was there before Huber. So Zellberg pioneered the study of a spectral theory of hyperbolic surfaces in 1950s, and then he celebrated Zellberg trace formula in 1956. We are not going into that direction, and connection with analytic and algebraic number theory and Zellberg conjecture to this day is open, which was stated in 1965. But so what is a small? So there is a number here, 1/4, which is not just any random number, is the bottom of the spectrum of upper half plane. So you can think of it's the infimum of the Rayleigh quotient over all compactly supported function. So for R2, this number is 0. For hyperbolic space, this number is 1/4. And a small eigenvalue are lambda I, such that its lambda I is strictly less than 1/4. So, I mean, we know that the H2 is the universal cover of any closed hyperbolic surface. So, so the eigenvalues below 1/4, we call them a small eigenvalue. And in this talk, we are interested in the behavior of these eigenvalues and how the geometry of a hyperbolic surface affect them. Okay, so this is our setting. So what we are interested is a bound for this eigenvalue. Among those, this particular is interesting because it's called the spectral gap. So in Michael McGee's talk tomorrow, and Bram, I think you talk about a three-dimensional hyperbolic surface. Some of the results that I mentioned about a small eigenvalue also true in higher dimensional hyperbolic spaces. So you will hear more about the spectral gap tomorrow, but we are interested about the whole collection here. Okay, so another things that we are interested is about number of these small eigenvalue, how many they are. Okay, so the first question is, do we have G such that lambda 1, so G is always hyperbolic, we are not leaving the hyperbolic setting, such that this, so for this less than 1/4. So maybe to many of you, the answer to this question is kind of obvious now, maybe not. But this question was not clear at all in 1972. McKean, in his paper, mistakenly stated that closed surfaces, hyperbolic surfaces, they don't have any eigenvalue below 1/4. And then in 1974, so Randall corrected this mistake. So here, the way that Randall answered that, he fixed this hyperbolic surface and built an n-sheeted cover and used Zelberg trace formula to show that for any, so Randall proved that for every natural number and sigma gamma, there exists a cover, a finite sheeted cover. So let's say n-sheeted cover such that lambda n is less than 1/4. So if we go up in the cover, we have as many small eigenvalue as we want. The price we pay is just the genus go up and up. There is a very simple geometric proof of that, but I think it appears in a survey paper by Ballman, Mathisen, and Mundell in 2018. So we come back to this geometric picture in the second half of the talk. And then and probably this is the proof that we may know. It's by Boozer in 77. So he showed that for every epsilon, there exists a hyperbolic metric on a given surface genus G such that lambda to genus gamma such that this is less than epsilon. So for every given surface of genus gamma, we can have at least 2 gamma minus 3 small eigenvalues. So how we build such surface? So we know that gamma 1 kind of measure the disconnect. If it's a small, it means that our space is almost disconnected. But here we have hyperbolic structure which add a little bit of rigidity. So then the question is that whether we can make our surface almost disconnected, and it's here. We need to know a little bit about hyperbolic geometry and building blocks. So let's make lambda 1 small. So if I have a surface of genus 2, so here if I cut along this closed geodesy, then I've got pieces which looks like trouser, they call pair of pants, And basically, any hyperbolic surface we can decompose to this building blocks. And if I can give you the length of these three closed geodesics which appear in the boundary of this pair of band, and they uniquely define one hyperbolic geometry on this piece. And then we can patch them together to build our surface. So here, if the length is L1, L2, L3, I have another freedom. So here, for pair of bands, I have L1, L2, L3, and then when I patch them together, then I can rotate, so I have rotation factor as well. So I have, for this surface, I have 6 dimensions of freedom to define my hyperbolic space. And then there is another important theorem, which is called Kolar theorem, which says that if I have a closed geodesic, I have a Kolar neighborhood around that. So if this is my, let's say, gamma I use for genus, so let's call it C, then I have a Kolar around that. So this Kolar is isometric to, so it has a width which relates to the length of my closed geodesic, and this width is isometric to minus W word product R divided by LZ. So it's a circle of length. So if the length of my geodesic is L, so we have kind of this cylinder type, but it's kind of a word product. The important thing is when L goes to 0, W, the width, goes to infinity. So if I shrink one closed geodesic, I have enough neighborhood around that. So I can, and we know that lambda 1, we can characterize it as infimum of the Rayleigh quotient of all of the function orthogonal to the constant on sigma. So let's build a test function. I can assume it's, so I go distance 1 away from my geodesic, plus 1 here, minus 1 here, and then I decrease, on this we decrease. And then here, with this kind of test function, which when this length shrink, the cylinder of width 1, the volume shrink to, so this goes to 0. And we can repeat this picture if I have more genus, so we do more shrinking. And what this number is, so we can decompose any surface of genus gamma to at most 2 gamma minus 2 pair of bands. So this is the restriction that we have. After that, there is no closed geodesic that they can pinch and get more. So every pair of bands is the Euler characteristic number is minus 1. So the Euler number of our surface is 2 minus 2 gamma. So this is how many pair of bands that we get. Okay. Any question? Okay, so we know at least we have 2 gamma minus 3, and then Wolpert, Shen, Yao, they wanted to understand the rate, in which rate they go to 0. So they obtained a nice formula connecting the rate of lambda k goes to 0 to the length of this separating geodesic. So they show that there is a topological constant times Lk, and here Lk for k between 1 to 2 gamma minus 3. So what is Lk? Is the minimum of the length of, so C is a multi-geodesic. So it's a collection, disjoint collection of simple closed geodesic. such that sigma minus c, if I remove this collection of the geodesics, has k plus 1 connected components. And then they show that for lambda 2 gamma minus 2, then if LK goes to 0, then we have a gap. Okay, so I come back to idea of the proof briefly, but so now you see that at least that many eigenvalue goes to 0. Here, the lower bound is depends on genus. So in around, when Boozer proved that, he also proved a lower bound for 4 gamma minus 2, but Schmitz and Boozer around in early 90s, they proved the following lower bound. So when we have a surface of genus 2, Schmitz proved that this is bigger or equal than 1/4, our magical number. But the way that he proved is very hand-on geometry of surface of genus 2 using the symmetry and some implication that is only available in that low genus. Boozer then improved this bound and showed that there is a uniform lower bound for lambda 2 gamma minus 2. And they conjecture that the lower bound should be 1/4. So this lower bound should be true for lambda 2 gamma minus 2. And this was open quite a while, and then it was proved by Otal and Rosas in 2009. So they proved the conjecture, Boozer-Schmitz conjecture, that this is strictly bigger than 1/4. So we have at most two, we can create at most 2 gamma minus 2, a small eigenvalue. We may have none, but yeah. So lambda 2 gamma minus 2 is strictly bigger than 1/4. Okay, so and the way they prove it, it's kind of, they use a very clever idea developed by Sevenak and Otal. So Sevenak studied the multiplicity of the first eigenvalue of Schrödinger operator and prove kind of Boursuq-Ulam lemma to control the multiplicity. And Otal proved that the nodal domain of eigenfunction has some topological non-triviality. And Otal and Rosas put this together to prove this lower bound. So extended the Sevenak result for multiplicity of first eigenvalue to obtain some bound on the count of dimension of eigenspace below 1/4. Okay, so so here I mentioned one more remark. So this lower bound since then has been improved in a series of papers by Ballman, Matheson, and Mondal. So between 2016 and 2018, there's a nice survey paper in 2018 that kind of overview the development and some of the direction. So this result is true in much more generality than the setting that I'm presenting. Okay, so going back to this family. So I just mentioned few development, and then I go back to the idea of the proof. And before going to start the second half of my talk, so in around 85, 88, Kulba and Burger, they study the asymptotic behavior of lambda k when this Lk goes to 0. So basically what they look at the kth eigenvalue of the surface, and they associate with the kth eigenvalue, assuming that this Lk is small, a graph. Can you see here from? Okay, so maybe I should avoid. Now it's okay. So they associated a graph based on this building block. So you have this Lk, which is realized by this multi-geodesic. You cut along this multi-geodesic, and then you consider the polar neighborhood of each geodesic in this collection. And then for the complement of this collar, you assign vertices, and the wedge of the volume of the collar will be the weight that you put on the edges. So basically, you assign a weighted graph that kind of capture the behavior, and then they show that this, if Lk goes to 0, and then lambda k plus 1 doesn't go to 0, then this goes to a limit. But as a consequence, which is stated, I think probably it's in paper by Bourget, that for lambda 1 and also consequence of the same work is that lambda 1 over L1, when lambda 1 is the length of our separating geodesic, but C is simple closed geodesic, then this is between an explicit topological constant plus L1 log L1, and then the same minus some other constant, the square root of L1. So we have the leading term, which is very explicit. It's the quotient of the Euler number of the surface divided by the Euler number of each piece that this simple closed geodesic cut.
Again, what is the C gamma?
So C gamma is minus chi of sigma gamma. So I'm not sure if maybe 2 pi squared or some constant, and here you have gamma plus and chi of gamma minus. So this cuts the surface to 2 pieces, so the product of this. So it's order 1 over gamma, in a sense, because you have 2 gamma minus 2. This is kind of almost half of the genus, almost. So you have gamma squared here. So if genus is high, it's like 1 over gamma. And then more recently, Nadine Gross and Melanie Rupflin, in 2019. So this was by this graph analogy. They use kind of holomorphic quadratic form and some complex analysis, because we are in dimension 2. I try to not write, so maybe I write it here. They show that actually this L1 log L1 is the actual the error term, so minus C gamma. This is less or equal, and so they improve the lower bound. But under the same condition that C is still simple closed geodesic, which is not always the case. So if we this separating geodesic is a multi-geodesic, then they may shrink with different rate, and that causes problem. So if the shrinking along this separating geodesic has a different rate, then we don't get this clean formula. But then Chaudhary and Ruflin in 2021. Chaudhary was the PhD student of Ruflin, so the result is in his PhD thesis. Is it okay or not? Okay. So they extended to lambda k under some condition, but I just write. So if you multiply here by L1 is lambda 1 minus C gamma L1 less than something. So here they prove that if Lk is L of C and C is the union of this Bi and Li is the length of Bi, then this F depends on this Li individually, so to capture the different rate that they may shrink, and then here we have some constant Lk square. So there is some condition that I'm not going to explain. Okay.
That bound also seems better than the first one, right?
Pardon me?
That bound also seems better than the first one, right? The log is gone.
The log one. So yes, yeah, but I mean here we have more condition. So I didn't mention the condition. So yeah, and also like the description of this functional. Yeah, but if you apply it, so it's more general and kind of improves it. Okay. So now I want to briefly talk about the idea of the proof of the lower bound. So for upper bound, we already have the an idea, because when we want to prove some upper bound, is always we look at the min-max. So for upper bound, so now idea of the proof of this inequality. So for upper bound, we use min-max of the Rayleigh quotient. So we need to find the nice test function, and we have everything that we want in our disposal. So we cut our surface along this C that has this length Lk, and then we yeah. So let me just write this. So the supremum is over all non-zero function in k plus 1 dimensional subspace. So this is k plus 1 dimensional subspace of H1 or C infinity, whichever you like. So we need to come up with k plus 1 test function to estimate lambda k. Our C that realized Lk already gives us k plus 1 connected component. We remove the collar, and then we put 1 on one of the components, 0 elsewhere, and then we decrease linearly in the collar, and we do this to obtain mutually disjoint support of test function, and then we use, so on this collar we have this Fermi coordinate around the center of the geodesic. So when I write this, I mean that metric in this will be the T2 plus cosh T. So we have like an explicit formula for the metric, and then the length of this.
The T is the one on the W.
The T is the R is the distance. So this is R, and T is this parameter. So
T is on the circle.
On the circle, and R is the distance from the circle. So So basically, for the upper bound, it's just using C and cutting along that plus and use the Polar neighborhood to build this test function. So upper bound, it's kind of simple and straightforward. Always the lower bound is the tricky part because, it's so how we get this lower bound. So the way that Schoenwolper-Yau approach the lower bound, they first prove a weaker inequality using Cheeger inequality. So let me just do it for lambda 1. So we have this famous Cheeger inequality where H is this isochromatic ratio. So if we look at all of the subdomain that has at most half of the volume and look at this isochromatic ratio, then we, so this is our Cheeger constant, and so this is Cheeger result that lambda 1 for any Riemannian manifold is lower bounded by that. So if you think of this quotient, so the maximum volume is in terms of genus gamma, right? So this is bounded above by genus. And this, so you can think of L1, so it's bounded below by L1. So what we get here is something like C of gamma L1 squared, not the power 1. So they first proved, used Cheeger inequality to get that, and then they made cases to improve the power to 1. But it's kind of doing cases by cases, looking at what could happen. But then a few years later, in 86 and 87, there was a very nice idea by Datsuk, and this is what we are going to use in the second half, or I will mention in the second. Datsuk, Pignatara, Randall. The first paper was by Datsuk, Randall, and then they extend also to finite volume surfaces, 4 of them Sullivan. 87. So they use 2 main ingredients. There is a very useful and well-known decomposition of hyperbolic surfaces, thick-thin decomposition. So they use the geometry and behavior of harmonic function or behavior of function that are solution to elliptic PDE. So what is thick-thin decomposition? So we can write our sigma as a union of thick part and thin part. So what is thick part? You can think of thick part as a, how I get this down? So the thick part is the part that we have control on the local geometry. So the thick part is the part that the injectivity radius is bounded below by a uniform constant independent of genus. So sigma thick is all part in sigma such that the injectivity radius of X is bigger or equal than this number. It doesn't matter. It has a name it's called, it's a constant, so we can do this decomposition for any hyperbolic space in higher dimension as well. And what is the thin part? So the thin part, it's collection of Kolar around BI, so where the length, so BI, where the length of BI is less than twice sinh of 1. So BI is a simple closed geodesic. So if you think of that picture, so the right and left, you can think of thick part, and then there is something in the middle that even though we don't control the injectivity radius, it can shrink, but we have information about the global picture of this color. We know that it's a word product, it's isometric to that word product. So either locally, exponential map gives us a diffeomorphism to Rn, or globally we know that it's word product. So the second idea that they use is, so if you have an eigenfunction, then the norm sup of that on a ball, okay, so that was not a good use of BI. I mean, I use BI for geodesic because later will be boundary geodesic, so here is the ball on a ball. This will be controlled by a first eigenvalue, so I put constant times lambda 1 or the corresponding, so Laplacian of phi is lambda 1 phi or lambda k phi, doesn't matter. Or let me first write like that. On the thick part, when ball, it's in the thick part, so sigma thick, then this is controlled by L2 norm of the gradient on a ball of twice as big as this ball. So, and when we have this inequalities, kind of, they show that then the oscillation on the thick part will be controlled by the first eigenvalue. If it's small, it's like we are almost constant on the thick part. So all of the energy. So we have the so if it's almost constant, then the Dirichlet integral should be somewhere on the thin part, non-zero. And here, when we calculate the lower bound, the length of this middle geodesic comes into play. Okay, so
and this, the callouts for the thin part, the width W, is it?
it is given explicitly in terms of L.
Okay.
Yeah, it's so the width in terms of L, it's something like sinh of 1 over sinh of L half, or maybe I'm missing something like that.
Something,
yeah.
right.
So we have kind of W. So it's not the action. So we have explicit formula for WL. So everything will be boiled down to.
And then you really get this covering of.
Yeah, so I mean here it's probably not clear, but the end of the thin part actually will be in the thick part. So the end of the collar, the injectivity radius on the boundary of the collar has injectivity radius bigger than sinh 1. So it covers all of the.
Thank you.
Okay, so I have not much time, so now I want to start the second half. And I want to paint the parallel picture and just mention the parallel result. So we see that the Laplacian is quite old classic. It started from the 50s and 1950s. The Steklov problem, so part 2, Steklov eigenvalues. So you will hear about the Steklov eigenvalues during this week, I think, as well. But, so let me just introduce it. So here, it's kind of very close to the Laplace eigenvalue, but now our setting, sigma, I slightly change. So I still compact hyperbolic surface, but now I want to have a boundary. So this is, so it's compact hyperbolic surface with B geodesic boundaries. So we have, so B is the number of boundary component, and each of them is connected, sigma is connected, but we have B boundary component. because our operator lives on the boundary. So the spectral parameter is on the boundary. So sigma is our spectral parameter. So it's called Dirichlet to Neumann operator. We take a function on the boundary, we extend it harmonically inside, we take the Neumann data or normal derivative along the boundary, and then we want to be proportional to u. So if you think of Laplacian as a kind of frequency of a vibrating drum, this is, you can think of the same picture, but the only difference is that all of the mass, so this is a drum that inside is kind of massless. All of the mass concentrated on the boundary. So it's so a Steklov problem describes vibrating a drum with all of the mass concentrate near the boundary, and can be mathematically kind of formulated. And there are a lot of interest and connection to other geometric problems, but let's now just continue with this theme. So we have discrete set of eigenvalue. Again, start with 0, constant function is connected. We have multiplicity 1. We have sigma 1. We may have some multiplicity. And then there is a number. But what is the magical number here? So the universal cover of closed surface is H2. But when we have boundary, the universal cover are not isometric to each other. It's a convex subset of H2 with geodesic boundary, but they are not isometric to each other. So we call it like bottom of the spectrum of sigma tilde. So in this unbounded case, Polymerakis showed that this is kind of well-posed problem, and this is equal to. So the Rayleigh quotient is almost similar, but on the denominator, instead of taking the integral over sigma, we take integral over the boundary, and this is compactly supported. And the question is that, do we have a small eigenvalue?
Asma, do you integrate on sigma or sigma tilde?
Oh, sorry, sigma tilde. Yeah, this is for sigma tilde. Thank you. So, do we have a small eigenvalues? I mean, if the answer was no, probably the second half is kind of pointless. So the answer is yes, but can you see why? So a small eigenvalue, we can again define like anything below the bottom of the spectrum of universal cover. So this question, with my colleague Sugata Oda, we explored this question, but it was motivated by a prior work where with Helen Green and Antoine Metras, we consider so-called low Steklov eigenvalue. So what is on hyperbolic surfaces? So what is low Steklov eigenvalue? And we show that how many they are, how many of them go to 0. But it doesn't answer the question quite. Okay, so what so this low Steklov eigenvalues was first, the study first started by work of Helen Green, and then we joined forces and kind of improve and complete the whole picture. So this is with Antoine Metras and Helen Green. This was prior to that date, but this is the published. So I need to. So instead of gamma, the role of genus, here the boundary component becomes important. So I define kappa to be b minus 1 if we have at least one genus.
Your G is gamma then?
Oh, yes, yeah. Gamma, yes. B, yeah, G for genus, but here I'm using G for metric. So, and here if gamma is 0, and if gamma is 0, then we have to have Euler characteristic number -1, then this should be, so this is kind of additional information that we don't need. So we have this kappa, and then we have beta, which is the maximum of, so if my boundary is B1 up to B, so this is maximum of the length of BI, and alpha is the minimum of the length. Okay. In the interest of time, let me just write the result when this constant L, this, which is very small when we are really shrinking. I will explain what it is. So in that case, sigma k, for k between 1 and kappa, is it between C, some universal constant over alpha times LK bar, and here, let me write it. I mean, we have a full result when we don't put this condition. So here, this depends on gamma and B. So here is a topological constant, here is universal constant. So it's kind of very similar to Shen-Wolpert-Yao, this inequality for this, and then sigma k, kappa plus 1, is between, so here I put C2, so we have this gap. So what is LK? I haven't defined what is LK bar. So this is the minimum of the length of multi-geodesic. So C is a multi-geodesic such that gamma minus C has K plus 1 connected components. And each connected component intersect boundary, and C intersection with the boundary is empty. So none of this geodesic, so it's collection of simple closed geodesic that they don't touch the boundary. I mean, it's not one of the boundary, and it's close, so it's not also reaching boundary orthogonally. And then, but each connected component contains one of the boundary component. So one thing that here is interesting, unlike so for the closed surface, this LK that I mentioned, it cannot go to infinity. It's the length. It's called Beer's theorem. The length of this LK for L2 gamma minus 3 is bounded by genus, but here the length can go to infinity. And because this is why I just write it for there. If I remove, then I need to take minimum between two things. So why it can go to infinity. So assume that this is very symmetric. I mean, all of this. So here. So if I wanna so here is 3 pieces. So I have 6 boundary components. If I wanna have 4 pieces, you can convince yourself that I have to separate one of these 2 boundary components, and I can make this very long. So this length can go to infinity, and so even here I can go up to B minus 1, but beyond L2, L3 can go to infinity. Okay, so
Can I ask
go
a
ahead.
question?
Yeah.
Is there division by beta missing on the left? Or something? Because beta can be arbitrarily large, right? On the right.
Is it beta or is it alpha? Is it what I want? No, that's correct. Because if beta is arbitrarily large, I mean here I didn't put the minimum things. Yeah, so I mean this bound comes from sigma k times the length of the boundary is bounded by a times gamma plus b times k. So here this is so here I can put sigma k times beta, and this is k is in terms of b, so it's coming from this upper bound. So this is the upper bound that we have.
I'm just confused by the fact that there's a topological constant all the way on the left.
Here.
There, yeah. See, because that thing.
Oh, okay. So sorry. Here I should have b and beta. I forgot. Yes. Thank you. Yes. Yes. Thank you. Okay. So we know that there is a collection that goes to 0, and then we have this gap. It's kind of we are painting the same picture as Shane Walker-Dio, but it still doesn't answer this. So any of you can answer, do we have a small eigenvalue? So actually the problem is that I cannot shrink in the middle and say that, okay, so it goes to 0, so we must have a small eigenvalue, because then the universal cover also is changing. So I have to kind of argue it's below the sigma naught of the new universal cover. So this Boozer geometric argument doesn't work in that setting, because we don't know if the universal cover is isometric, and this is work in progress with Sugata Mandal. So the first observation that we had is just if we look at Randall, the simple geometric proof of Randall, we can, so let me just show you. So if I have just one boundary component cut along a non-separating closed geodesic, so this is my boundary. I'm cutting along this non-separating. Now I have pair of paths, and then just connect. Look, this will be n-sheeted cover or 2 n-sheeted cover over this. So now divide on half. Here plus 1, here is minus 1. So sigma 1 is the infimum of the Rayleigh quotient over the boundary for f orthogonal to constant along the boundary. So half of that is plus 1 along the boundary, half of that is minus 1. Just here I need a little bit of a space to move from plus 1 to minus 1. I use the Kolar neighborhood of this geodesic. So this is controlled by constant, doesn't depend on the n-sheeted cover, but the L2 norm here, so for this sigma 1 of this n-sheeted cover of this surface, sigma 1, 1, goes to 0. But they both have the same universal cover, so we have a small eigenvalue. And what we are, okay, so I'm in the question part, so I just borrow 3 minutes and then I stop. So we show that the number of sigma 1, so we show that we can adapt Otal-Rosa's argument, and we get, so this is less or equal than minus the Euler characteristic number, which is 2 gamma plus b minus 2. But because of that picture, I mean, but here we didn't need to use the fact that the boundary is geodesic. This result is when the boundary is geodesic, so we have this picture. So we are hoping that, so we have some other result when we impose the geodesic boundary, which does not depend on gamma, but depends on other things, but it's not just B. So in the Laplace, I want to just end with one conjecture and maybe two results. So I said at the beginning that the small eigenvalue is kind of exceptional. So this is what you hear more about in Michael's talk tomorrow. So there is a very recent result by Anand, Taraman, and Monk in a series of 2 long papers, and a lot of breakthrough results in recent years, like about these random hyperbolic surfaces. So I'm not going to say what is the space, but with this coordinate with this length of pair of pants. And so here, if we put some measure, probability measure, on the moduli space of the closed surface, so they prove that lambda 1 of sigma gamma bigger than 1/4 minus epsilon for every epsilon. When we take the limit, we look at the hygienous regime. This is 1. So typically, we don't have eigenvalue below 1/4. And then with Laura Monk, we asked the same question about the Steklov problem. Is it, do we have the same picture? Can we say that there is nothing below, like, okay, so here we don't have such number because the cover are not isometric. So, and it turns out that it's a consequence of a result in a paper by Han Hee Hong 2024 that they prove. So so if here now we put Weil Peterson, whatever the measure is on the space of all hyperbolic metric that we can put on surface with gamma genus and B boundary component, and the length is prescribed. So then sigma 1 of this is bigger than some constant. So there exists C such that this is 1. So there is a constant. So it's kind of extension of Mirzakhani's result for the first result in this sequence that leads to that result for a Steklov. And our conjecture, so I end with that conjecture that for sigma 1 is for every epsilon in hygienous regime, this is 1. And the optimal constant, we believe, should be 2/pi. So I leave that to question. And 2/pi is the bottom of the spectrum when I put a Steklov here, and I solve the Dirichlet to Neumann, bottom of the spectrum of the Dirichlet Neumann, and this half. Okay, sorry for running.
So we do have time for questions or comments, please.
Is there a graph analog for what you showed for also for the Steklov operator?
Oh, the graph analog. So,
Or
yeah.
not graph analog, but a graph,
about the rate.
a graph that you can decompose and compare the rates.
Yeah, so there is something that Bruno and some colleague are working to, but it's not as, I mean, there are a discrete version of a Steklov problem on graph, but whether this capture or control the rate is the question to be answered, yeah. Yeah.
Do you know something about sigma naught of the universal cover for a random surface?
sigma. So we believe that this is the lower bound because why is the case? So when because the half color near the boundary, the width will be of order 1/2 of log gamma. So when gamma goes to infinity, the width goes to infinity, so we are in this picture. So this is why we believe 2/pi is there. But there is no trace formula or no way to approach this. So yeah.
Questions, comments?
Sorry, but it's this work of Anata Raman and Monk looks like what in graph theory is called the Alon-Bopana.
But they use also trace formula for the cancellation, etc. So,
but I wonder, like in graph theory, there's a huge business, very successful business of creating things that achieve this bound, like deterministic objects. I wonder if
for the discrete version of
I wonder if
this for so then I'm not sure what would be the right picture because.
No, I'm not asking about the discrete. I'm asking about this. Are there any works that achieve a sequence of surfaces with growing number of genus that actually get arbitrarily close to this bound?
To this bound, Brown, I think.
No, it's a big open problem. So Asma mentioned Selberg's conjecture, which is basically the analog of saying that Lubotsky-Phillips-Sarnak Ramanujan graphs have optimal spectral gap. The analog in parabolic surfaces is basically Selberg's conjecture.
Yeah.
So we don't know.
But there is no analog of Lubotsky-Phillips-Sarnak
There's an analogous construction of surfaces, but
There
we
is?
don't know how to prove that they have.
You're asking about Steklov Eigenvalues?
No,
No,
about the
that's,
Laplace,
the original.
about the
No. So there is a construction
There is a construction, but we don't know how to prove that it has optimal.
that is optimal, but there is a construction that's optimal. Thank you.
Any more questions? Okay, thank you very much again.